Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through 100 facts about the universe, not as a list of isolated curiosities, but as pieces of one connected history, a history written in light, gravity, matter, and time. For now, imagine that you are sitting beside the wide observation window of a spacecraft in orbit above the night side of Earth. The cabin lights have been lowered. Beneath you, the planet is a dark curve traced by the faint glow of its atmosphere, while beyond the glass the moon hangs in sunlight, quiet and sharply outlined. The moon appears close enough to feel almost immediate. Yet even this familiar view belongs to the past. The light now entering your eyes left the lunar surface roughly 1.3 seconds ago. If someone could switch on a powerful lamp on the moon, you would not see it at once. The signal would cross the distance between the moon and your window before the change became visible. Astronomy begins with this small delay. Nothing in the sky is seen exactly as it is now. Turn away from the moon and choose a bright star. Its light may have traveled for years, decades, or centuries. Look toward another galaxy, and the journey can stretch across millions or billions of years. Distance becomes a kind of time machine, although not one that carries you into the past. Instead, the past comes to you, delivered by light that has been traveling since long before your observation began. This means that the sky is not a single moment. It is a mosaic of different ages. The moon is seen seconds ago. The sun, if it were visible from this side of Earth, would be seen about 8 minutes ago. Nearby stars appear as they were years ago, while distant galaxies reveal eras that ended before Earth existed. Every direction carries a different delivery time. The comparison is useful, but it has limits. Light crossing an expanding universe does not travel through an unchanging postal map. Over immense distances, the expansion of space stretches wavelengths, and astronomers must distinguish among several ways of defining cosmic distance. Even so, the central fact remains simple. To look outward is always to receive earlier information. Now allow your eyes to adjust to the darkness beyond the window. More stars slowly become visible, but the sky never fills completely. Even under exceptional conditions, far from city lights and with a clear atmosphere, an unaided observer sees only a few thousand stars at one time. The exact number depends on eyesight, location, season, atmospheric clarity, and how faint a point of light can still be detected. It is an impressive view, but it is a remarkably selective one. Most of the stars in the Milky Way are missing from the scene. They have not disappeared. Your eyes simply cannot collect enough of their light. Some are too distant. Others are hidden behind lanes of interstellar dust. Many shine most strongly at wavelengths human vision cannot detect. And a vast population consists of red dwarfs, small, cool stars that can remain active for extraordinary lengths of time, yet glow so faintly that even relatively nearby examples are invisible without a telescope. If you tried to describe the galaxy using only the stars visible through the window, you would receive a distorted picture. The brightest points would seem common because they are easy to notice, while the much larger population of dim stars would nearly vanish from your account. Astronomers call this kind of problem a selection effect. What can be observed is not always a fair sample of what exists. Imagine bringing a modest telescope to the glass. fainter points appear. Increase the aperture, and the instrument gathers more light, revealing objects your pupils could never register. Exchange visible light detectors for infrared sensors, and some dusty regions become more transparent. Radio antennas, ultraviolet observatories, X-ray telescopes, and gamma-ray instruments each uncover a different part of the same universe. The sky changes because the method of seeing has changed. This is one of astronomy's quiet corrections to ordinary experience. Human vision occupies only a narrow band within the electromagnetic spectrum. The night sky looks the way it does partly because our eyes evolved for life beneath the sun, not for making a complete inventory of the cosmos. Darkness can therefore mean that no visible light is arriving in sufficient quantity. It does not necessarily mean that nothing is there. Let the spacecraft turn slowly until the Milky Way stretches across the window. In a truly dark sky, it appears as a pale, uneven band built from the combined glow of stars too numerous and too faint to separate with the naked eye. Dark seams divide that glow. At first, those gaps may look like openings in the galaxy, but many are clouds of dust blocking visible starlight from more distant regions. The absence of light becomes evidence of material lying in the way. Yet a larger question remains. If stars and galaxies extend throughout the cosmos, why is the entire night sky not bright? Why do broad regions remain black between the points of light? This puzzle is often called Olber's paradox. Consider an idealized universe that is eternal, static, infinite, and filled uniformly with shining stars. In such a cosmos, almost every line of sight should eventually end on a stellar surface, just as nearly every direction inside a sufficiently dense forest eventually meets a tree trunk. More distant stars would look smaller and fainter, but each spherical shell of space would contain more of them. Under those assumptions, the combined light would make the whole sky glow. Our universe does not satisfy those assumptions. It has a finite observable history. Light from arbitrarily distant regions has not had unlimited time to reach us. Stars have not been shining forever, and their populations change as galaxies evolve. Cosmic expansion also stretches the wavelengths of traveling light, reducing the energy with which very distant radiation arrives. Together, the history and expansion of the cosmos prevent the simple, static prediction from becoming reality. Interstellar dust cannot solve the paradox by itself. Dust can absorb visible light, but absorbed energy warms the grains, which then radiate at other wavelengths. Given enough time in an eternal static universe, the obscuring material would heat until it returned the energy it received. Dust can hide particular stars from visible view, as it does along the Milky Way, but it cannot explain the darkness of the sky as a whole. From your place above Earth, that darkness now carries a different meaning. It is not merely an empty background placed behind the stars. It records the limited travel time of light, the finite lives of luminous objects, the evolution of galaxies, the expansion of space, and the narrow sensitivity of human eyes. A black interval between two stars may contain dust, faint suns, distant galaxies, invisible wavelengths, or light that has not yet had time to arrive. The view through the window is therefore both real and incomplete. Every visible point is a messenger from an earlier moment, while every dark region reminds us that observation has boundaries. The universe does not present itself all at once. arrives gradually, photon by photon, filtered by distance, time, matter, motion, and the instruments we use to receive it. Soon, we will follow those instruments beyond the stars that human eyes can see. They will lead us toward a glow that does not come from any ordinary sun. Light released when the young universe first became transparent, stretched across cosmic history until it reaches us today as microwaves. The darkness outside the spacecraft is not the end of the view. It is where a deeper image begins. Keep your place beside the spacecraft window, but imagine that the glass is no longer your only way of seeing. The ship carries an instrument able to detect microwaves arriving from every direction. When its map appears on a screen, the familiar stars disappear. The Milky Way can be accounted for and carefully separated, and behind its local glow, another light remains, a nearly uniform background spread across the entire sky. This radiation does not come from a shell of stars surrounding you. It began its journey before any star had formed, before galaxies had assembled, and before planets or familiar chemistry were possible. It is called the cosmic microwave background, or CMB, and it is the oldest freely traveling electromagnetic radiation that astronomers can observe directly. To understand why this light is so ancient, let the imagined journey move backward through cosmic history. Galaxies draw closer together. Stars vanish because you have reached an age before their birth. The universe becomes hotter and denser, filled not with neutral atoms, but with an ionized plasma of nuclei, electrons, and radiation. In that environment, light could not travel far in a straight line. Photons repeatedly encountered free electrons and scattered in new directions. The effect was not the same as ordinary mist, yet a glowing fog is a useful first comparison. In fog, light scatters from droplets. In the young universe, it scattered mainly from charged particles. Either way, a distant view was hidden because radiation could not move freely across large distances. Expansion gradually changed those conditions. As the universe grew, it cooled. Roughly 380,000 years after the beginning of the hot, dense phase, temperatures fell enough for electrons to remain bound to nuclei in large numbers. Neutral atoms could persist. With far fewer free electrons available to scatter photons, the cosmic fog cleared and radiation began traveling across space with much less interruption. The word recombination is often used for this transition, although the prefix can be misleading. It does not mean that these electrons and nuclei had necessarily been combined before. It describes the formation of neutral atoms during a period when the universe was becoming transparent. Photon decoupling is a related name for the point at which radiation stopped interacting so frequently with matter and began to stream freely. Neither process happened everywhere in one perfectly sharp instant. Conditions changed over an interval, and the light now reaching your detector last scattered across a layer with a finite thickness in time and space. The CMB is therefore not a flash from a single wall. It is the surviving radiation from an extended transition. When those photons began their long journey, their wavelengths were much shorter and the universe was far hotter than it is now. Cosmic expansion stretched the radiation as space evolved. By the time it reaches the spacecraft, it has been shifted into microwave wavelengths and cooled to only a few degrees above absolute zero. The word cooled refers to the radiation spectrum, not to individual photons feeling temperature as an object would. When astronomers measure that spectrum, it follows the shape expected from an almost perfect black body. Radiation with an extraordinarily precise thermal distribution. This is one of the strongest pieces of evidence that the early universe passed through a hot, dense state. At first glance, the microwave map looks almost featureless. That smoothness is itself remarkable. Regions now separated by enormous distances began with nearly the same temperature. Yet the map is not perfectly uniform. Magnify the scale and apply a color range sensitive enough to reveal tiny differences, and faint, warmer, and cooler patches emerge. These variations are extremely small, measured in millionths of a degree. They reflect a combination of early differences in density, motion, and gravitational potential. The CMB does not show tiny, completed galaxies waiting to grow larger. It shows subtle physical variations in the young universe, variations that gravity later amplified as matter gathered into stars, galaxies, clusters, and the cosmic web. Several generations of space missions transformed this faint glow into a precise scientific record. COBE established the extraordinary black body spectrum and detected large-scale anisotropies. WMAP mapped the temperature pattern with much greater detail. Planck sharpened the view again, measuring temperature and polarization across a wide range of angular scales. Each instrument observed microwave intensity rather than taking an ordinary photograph. Researchers cleaned foreground emission, calibrated detectors, compared frequencies, and reconstructed a map of ancient radiation. Calling the result a baby picture of the universe can help, provided the comparison is not taken literally. The pixels do not show baby galaxies or a visible landscape. They encode tiny differences in the temperature and polarization of light released during the era when the cosmos first became transparent. Imagine holding two images beside each other. One is the dark sky from the spacecraft window, scattered with nearby stars. The other is the microwave map, covering the same directions but recording a time before those stars existed. The maps overlap on the sky while belonging to radically different ages. One shows the relatively recent universe through visible light. The other preserves conditions from its early history. There is an important boundary here. The CMB is the oldest light that travels to us freely, but it is not the oldest event and not the beginning of everything. Earlier processes left indirect traces in the radiation and in the later distribution of matter. Yet the plasma itself prevented ordinary photons from bringing us a clear picture from deeper times. Looking farther with a visible or microwave telescope cannot simply reveal an earlier luminous surface behind it. The universe has given us a record, but not an unrestricted view. We infer what happened before transparency by combining this radiation with nuclear physics, particle physics, gravitational theory, and the later structure of the cosmos. The oldest light is powerful precisely because it carries so much information while also marking the limit of direct electromagnetic sight. Now let the microwave map remain on the screen as time begins moving forward again. The tiny variations grow, matter falls toward slightly denser regions. Gravity works slowly but persistently, and the nearly smooth young cosmos begins to acquire structure. What first appeared as faint mottling will eventually become a network spanning distances so vast that entire galaxies look like points along its threads. Imagine the spacecraft moving forward through billions of years while its display follows the growth of those early variations. The nearly uniform background develops texture. Denser regions draw in more material. Small structures gather into larger ones, and the once subtle pattern becomes a three-dimensional network of filaments, sheets, clusters, and broad, underdense spaces. This is the cosmic web. It is not a material net suspended in emptiness, and no one designed its intersections. It is the large-scale result of gravity acting on an uneven distribution of matter in an expanding universe. On the display, galaxy clusters shine like cities at busy junctions. Long filaments connect them, carrying groups and galaxies across immense distances. Between the bright roots lie voids, regions containing much less matter than the cosmic average. They are not perfectly empty. Faint galaxies, gas and dark matter can remain within them, but compared with the crowded filaments, they are quiet territories. The exact size assigned to a void depends on how a survey samples galaxies and how researchers define its boundary. Some span tens of millions of light-years, while larger examples can extend much farther. A single dramatic size should never be treated as the standard for every void. The reliable idea is the contrast. Matter has gathered preferentially into walls, filaments, and nodes, leaving other regions increasingly underdense. Visible matter alone cannot explain this architecture. The clue appears first on smaller scales. Aim the spacecraft toward a spiral galaxy and measure how quickly stars and gas orbit at different distances from its center. If only the luminous matter provided the gravity, the outer region should often move differently from what astronomers observe. Instead, many galaxies behave as though additional unseen mass surrounds and permeates them. Now place a massive galaxy cluster between the ship and a more distant field of galaxies. Light from the background does not always travel to you along an apparently straight path. The cluster's gravity curves space-time, bending and distorting the images behind it. By measuring arcs, stretched shapes, and statistical patterns of gravitational lensing, astronomers can estimate how mass is distributed, whether that mass shines or not. The same missing component appears in cluster motions, in hot gas held by cluster gravity, in colliding systems, and in computer models of structure growth. These are not identical measurements repeating one assumption. They are different observations pointing toward more gravitating mass than ordinary luminous material can supply. Dark matter is the name given to that unseen component. The term describes what it does not appear to do. It does not emit, absorb, or reflect ordinary light in the usual way. Its presence is inferred mainly through gravity, somewhat as invisible wind can be inferred from the motion of leaves. The analogy stops quickly, because wind is familiar matter and can be sampled directly. The motions of stars and the bending of light reveal dark matter's influence without yet telling us what particle or physical entity produces it. That distinction matters. Evidence for unseen gravitating mass is strong, but no single astronomical observation identifies a particular dark matter particle. Many candidates have been proposed, and sensitive experiments search for interactions beyond gravity. So far, the underlying nature remains open. Modified theories of gravity offer another line of investigation. Some can reproduce parts of galaxy behavior without the same dark matter assumptions, but a successful alternative must explain more than rotation curves. It must also account for lensing, galaxy clusters, colliding systems, the CMB, and the way structure developed across cosmic time. The full collection of evidence is the difficult test. In the standard cosmological model, dark matter provides much of the gravitational framework on which galaxies and clusters assemble. It is not rigid scaffolding, yet the comparison captures a useful contrast. Ordinary gas can cool, collide, and form stars, while dark matter gathers gravitationally without shining or dissipating energy in the same manner. Dark energy is a different mystery. It is associated with the observed acceleration of the universe's late-time expansion, supported by several kinds of measurement, including distant supernovae, the CMB, baryon acoustic oscillations, and studies of structure. Dark matter clumps and helps form the web. Dark energy, in the simplest standard model, remains comparatively smooth and affects the evolution of cosmic expansion. The similar names conceal very different problems. Model-based estimates often divide the cosmic energy budget into a small share of ordinary matter, a larger share of dark matter, and a dominant share assigned to dark energy. Those proportions depend on the cosmological model used to interpret the measurements. They are not a direct inventory made by placing the universe on a scale. What remains secure is the humbling imbalance. The atoms that make stars, planets, oceans, instruments, and observers are only a minority of the total described by the standard model. Return to the ship's map and remove every glowing galaxy. Much of the underlying gravitational pattern would remain. Put the galaxies back, and they trace the densest portions like lights along roads at night. This is why surveys of millions of galaxies can reveal structure that no single image could show. Each measured position adds 1 point to a map far larger than human vision. The web also preserves history. Its filaments did not appear fully formed. Gravity amplified the early variations recorded in the CMB. Denser regions attracted more matter, becoming still denser relative to their surroundings. Underdense regions lost material toward their boundaries and grew emptier by comparison. Expansion influenced the scale of the process, while gravity built local and regional structure. Nothing in this story requires matter to know where it is going. Tiny differences, physical laws, and enormous spans of time are enough. From near uniformity emerged a universe with preferred gathering places, long connecting structures, and vast, quieter regions between them. As the spacecraft follows one filament toward a bright node, separate points resolve into galaxies. Some are moving toward one another. Their shapes are already distorted by mutual gravity. The invisible architecture has guided you toward a slower transformation. Galaxies meeting, merging, and rebuilding themselves without behaving like solid objects in collision. Ahead of the spacecraft, two galaxies approach across a distance that still appears enormous. Each contains billions of stars, clouds of gas and dust, stellar remnants, dark matter, and a central region shaped by its own long history. From far away, their meeting may look like two luminous bodies on a collision course. Up close, the event is stranger and much more spacious. A galaxy is not solid. Its stars are separated by distances so great that when two galaxies pass through one another, direct collisions between individual stars are exceedingly rare. The systems interpenetrate more like sparse swarms than like stones striking each other. Gravity, however, reaches across all of that space. As the galaxies draw near, their combined fields alter stellar orbits on a vast scale. Stars that once followed relatively settled paths can be thrown into elongated loops, broad shells, or sweeping tidal tails. The galaxies may pass apart and return several times before finally settling into one remnant. Imagine following a single star during the encounter. It will probably never touch another star. Yet its path can change completely because the gravitational landscape around it is changing. The star may end in a wider orbit, move toward the new center, or be cast into a faint outer stream. A merger can transform a galaxy without most of its stars physically colliding with anything. Gas behaves differently. Interstellar clouds can shock, compress, lose energy, and flow. In some encounters, compression encourages bursts of star formation. In others, gas is stripped outward or funneled towards central regions. The outcome depends on the masses, gas content, relative speed, orientation, and environment of the galaxies involved. Gas driven toward a galactic center can also feed a central black hole. As material spirals inward, it heats and may produce a luminous active galactic nucleus. The black hole is not swallowing the entire galaxy like a vacuum cleaner. It is consuming a small fraction of material whose orbit has been disturbed enough to carry it toward the center. Energy released by that accretion can in turn heat or expel surrounding gas, influencing later star formation. Not every merger produces the same display. A meeting between gas-rich galaxies can look very different from one between systems dominated by older stars. Some encounters create brilliant but temporary starbursts. Others mainly rearrange existing stellar populations. The word merger names a family of histories, not one repeatable explosion. This is why the ghostly swarm analogy must be handled carefully. It works for the widely separated stars, but not for the gas. The luminous systems can pass through each other while their diffuse material interacts strongly, producing turbulence, heating, and new patterns of collapse. Watch the encounter over hundreds of millions of years, and the dramatic shapes gradually soften. Tidal tails may remain as evidence. Stellar populations become mixed. New stars add their light to older ones, and the final galaxy can look very different from either parent. A merger is not a single crash. It is a long gravitational negotiation. Smaller encounters are common as well. A large galaxy can gradually pull apart a dwarf companion. The smaller system stretches under unequal gravitational forces until some of its stars escape into long, coherent streams. These trails resemble loose threads drawn from cloth, although the stars are not connected and the structure unfolds in 3 dimensions. Astronomers find such streams around the Milky Way. They are records of past and ongoing accretion, allowing researchers to reconstruct portions of our galaxy's history from the motions and chemical signatures of dispersed stars. The Milky Way also continues to interact with dwarf companions, including the Magellanic Clouds and the Sagittarius system. Our galaxy is not a finished island. It is still responding to its surroundings. Mergers are only one way galaxies grow. Fresh gas can flow inward from the larger cosmic environment. Stars can form within a galaxy from its existing gas supply. Small companions can be absorbed, and major encounters can combine systems of more comparable size. The importance of each pathway changes with cosmic era, environment, and galaxy mass. Even a galaxy that appears calm may therefore contain evidence of upheaval. A faint halo can preserve ancient streams. Groups of stars with unusual motions may share an origin in a swallowed companion. A disk can carry bends, waves, or asymmetries created by an encounter whose visible partner has already been dispersed. The spacecraft now enters the outer halo of the merging system, remaining far from any star. Around you, the scene would not resemble the dense blaze shown in artistic illustrations. Most directions would still look dark. The galaxies are enormous because their stars are spread through immense volumes, not because every region is crowded. From this position, the slow pace becomes apparent. Human lifetimes capture only snapshots. Astronomers compare many systems at different stages and use simulations to connect those observations into an evolutionary sequence. One pair has just begun to distort. Another displays long tails. A third has a bright central remnant and fading debris. Together, they reveal a process too long to watch from beginning to end. Simulations allow gravity, gas dynamics, star formation, and energetic feedback to unfold faster than cosmic time, but they are not recordings of a particular galaxy's future. Researchers test them against observed shapes, motions, gas distributions, and stellar ages. Agreement across those clues can support a history without pretending that every detail is uniquely known. Mergers also remind us that classifications are temporary. Spiral, elliptical, dwarf, irregular. These names describe structures observed during particular phases. Gas arrives, stars form, orbits change, and environments exert pressure. Galaxies carry recognizable identities, but those identities evolve. As the encounter continues, step back until both systems once again become points within the cosmic web. Their local motion is governed by mutual gravity, not simply by the expansion of the universe. Bound objects and interacting neighbors do not behave like marks passively carried apart by a stretching sheet. This distinction will matter as the spacecraft turns toward more distant galaxies. Nearby motions can be complex. Some systems approach, some orbit, and some fall into clusters. Only across sufficiently large scales does a broader pattern emerge, a relationship between distance and cosmological redshift that reveals how the scale of the universe changes with time. Let the merging galaxies fade behind you and choose a new set of targets. The spacecraft's instruments identify galaxies at many distances, measure characteristic patterns in their light, and compare the wavelengths received with the wavelengths produced by the same atoms in laboratories. In many distant galaxies, those patterns arrive shifted toward longer, redder wavelengths. The shift is not simply a change in color that human eyes would notice. It is a proportional stretching of the entire spectral pattern, visible in precise lines associated with hydrogen, oxygen, calcium, and other elements. Redshift by itself is not a universal tape measure. Astronomers connect it to distance through a cosmological model and compare it with independent methods. Objects whose intrinsic brightness can be estimated, characteristic physical scales preserved in the distribution of matter, and geometric relationships available in suitable systems. Each method carries uncertainties, so the expansion history emerges from overlapping evidence rather than one translated color. Across sufficiently large scales, more distant galaxies generally show larger cosmological redshifts and larger inferred recession rates. This is the Hubble-Lemaitre relation, one of the observations that transformed the universe from a seemingly static arena into an evolving system. The pattern is statistical, not a perfect rule for every nearby galaxy. Local gravity produces peculiar velocities, motions relative to the average cosmic flow. The Andromeda Galaxy, for example, is approaching the Milky Way because the two belong to a gravitationally interacting region. Galaxies inside clusters orbit within their shared gravitational field. At modest distances, these local motions can obscure the broader expansion pattern. Move far enough outward, average across many systems, and the larger trend becomes clearer. Distance and redshift rise together. The universe is not expanding from a central location that can be marked on the spacecraft's map. Observers in other galaxies would measure the same broad pattern around themselves. The familiar image of raisins separating in rising dough can illustrate this absence of a unique center. Every raisin sees more distant raisins receding more quickly as the dough expands. But the comparison carries several traps. A loaf has an edge, a center in an external room, and dough-filling space between the raisins. The universe need not share those features. The analogy demonstrates a relationship among distances, not the literal substance or shape of reality. A changing map scale offers another way to imagine the process. Suppose the coordinates between widely separated, unbound locations change their physical scale with time. No galaxy needs a rocket pushing it through a surrounding emptiness. The geometry used to describe separation evolves, and light traveling across that evolving geometry arrives with its wavelength stretched. This is cosmological redshift. It differs conceptually from the ordinary Doppler shift produced by motion through local space, although both can alter observed wavelengths and can be described together in appropriate calculations. Over cosmic distances, redshift carries information about how much the scale factor changed while the light was traveling. Return to the observation window and imagine a wave crest leaving a distant galaxy. Another follows it, then another. During the journey, cosmic expansion increases the separation represented by those crests. When they reach the detector, the wavelength is longer than when it was emitted. Higher energy light can shift into lower energy bands, sometimes moving out of visible wavelengths entirely. It is tempting to say that space behaves like rubber being stretched. That phrase can help briefly, but space is not a material sheet with tension, thickness, or molecules. Galaxies are not glued to fabric. Metric expansion is a statement about the evolving geometry of large-scale distances in cosmological models. Nor does expansion act as a simple local force pulling apart everything. atoms remain bound by electromagnetic interactions. Planetary systems remain governed by gravity and motion. Galaxies and many galaxy groups hold together. A ruler does not lengthen merely because the cosmic scale factor changes, and the spacecraft does not swell as it travels. Expansion becomes dominant when considering sufficiently large separations between systems that are not gravitationally bound to one another. This separation of scales protects ordinary structures while allowing the distance between remote galaxy groups to grow. The rate of that growth is an active area of measurement. Different methods for estimating the present expansion rate do not converge perfectly on one value. Observations of the nearby distance ladder and inferences based on early universe data produce a well-known tension. It may reflect unrecognized measurement effects, details of calibration, limitations in the standard model, or some combination not yet understood. The phrase present expansion rate can also hide a history. A measurement made nearby samples the relatively recent universe, while early universe inferences begin with ancient conditions and evolve a model forward. Comparing them tests not only instruments, but the assumptions connecting one cosmic era to another. For this journey, no single number needs to be declared final. The important fact is that the disagreement is scientifically productive. Precision has become high enough that a relatively modest mismatch demands explanation. Cosmology advances not only when measurements agree, but when careful methods refuse to fit together as expected. The history of expansion also changed. Evidence from distant Type 1a supernovae, baryon acoustic oscillations, the CMB, and structure studies supports the conclusion that late-time expansion is accelerating. Dark energy is the standard label for whatever component or effect accounts for this behavior in the prevailing models. The name does not identify a discovered substance or settle the underlying physics. Imagine two remote galaxy groups with no gravitational bond between them. As cosmic time passes, their separation can grow at an increasing rate, even while every galaxy inside each bound group continues following local orbits. Large-scale acceleration and local stability coexist because they apply across different physical regimes. Now look back toward the light received during the journey. A distant galaxy appears not where it is today, but where and when its photons began traveling. Expansion changed the route while the source continued evolving. The map on the ship is therefore a map of both position and history, reconstructed through a cosmological model. Every measurement has a horizon beyond which information has not reached the observer. That limit is not marked by a wall or a final galaxy. It arises from light travel time, expansion history, and causality. To understand it, the spacecraft must stop pretending that the observable universe is a single sphere shared from one privileged center, and instead ask what any observer, anywhere, is able to receive. Imagine switching off the spacecraft's engines and sending a brief pulse of light in every direction. The signal moves outward locally at the speed of light. At the same time, radiation from past events continues arriving at the ship. Together, these incoming and outgoing paths define what can influence you and what you may influence, constrained by the geometry and history of space-time. Your observations belong to a past light cone. The phrase describes the collection of events whose signals have had time to reach your present location. Nearby events can be recent. More distant ones must have occurred earlier. The farther the ship looks, the deeper the received information extends into cosmic history. This does not make the spacecraft the physical center of the universe. It makes the spacecraft the center of its own observable region, just as every observer occupies the center of theirs. An astronomer in a galaxy billions of light years away would construct a different past light cone around that location. Some regions visible to that astronomer might be inaccessible to you, and some visible to you might lie beyond that observer's present reach. Think of each observer surrounded by a personal domain of arriving news. The comparison helps explain why the observable universe is centered on whoever performs the observation. Yet the boundary is not a circular fence, and space-time is not a flat sheet. The true geometry is four-dimensional, and its causal limits evolve. Several horizons appear in cosmology, and they answer different questions. The particle horizon concerns the greatest distance from which signals could have reached an observer during cosmic history up to the present. It marks a limit to current observation, given the age and expansion history of the universe. Because large-scale distances changed while the signals traveled, the present cosmological separation associated with that horizon is not simply the age of the universe multiplied by the speed of light. This is one reason phrases such as a 13 billion light-year sphere can mislead. Light travel time, current separation, and the distance inferred from brightness are related, but they are not interchangeable labels. The Hubble sphere is different. It is associated with the distance at which recession in the smooth Hubble flow reaches the speed of light at a given cosmic time. It is not always a permanent barrier to observation. Depending on how expansion changes, light emitted from beyond that scale can sometimes enter a region from which it eventually reaches us. A cosmic event horizon asks another question. From which events emitted now or in the future could a signal ever reach a particular observer, given the future expansion history? Its existence and behavior depend on the cosmological model. In an eternally accelerating scenario resembling the simplest dark energy model, some presently observable systems can eventually become unreachable by signals emitted at sufficiently late times. These distinctions matter because a horizon is often mistaken for an edge. The observable limit is not evidence of a physical wall surrounding all reality. It is a limit on connection and information. Standing on a shoreline, you can see only to a visual horizon, but the world does not end where the view ends. The cosmic case arises for different physical reasons, yet it carries the same warning. The boundary of observation should not be confused with the boundary of existence. Nor is every object near a horizon forever fixed there in one simple picture. Horizons depend on the full space-time model and on the observer's question. A light ray can initially be carried away from us by expanding distances and later make progress toward us if the expansion history changes appropriately. Causal diagrams help physicists track these paths without treating recession speed as ordinary motion through a static arena. The ship cannot travel to the particle horizon and touch it. If the spacecraft changed location, its observable region would change as well. The horizon is defined in relation to an observer and a cosmic history, not as a material surface fixed at one address. Expansion also makes the present distance to ancient sources more subtle than a simple multiplication of light travel time. Radiation can spend billions of years crossing space while the scale of large distances changes. The source's current cosmological distance can therefore be much greater than the number of years its light has traveled would suggest. Different distance definitions are useful for different measurements, and none should be inserted casually into an everyday map. Now ask whether the entire universe is finite or infinite. Measurements of the CMB indicate that the geometry of the observable region is very close to spatially flat on large scales. Parallel lines and triangles in such a geometry behave approximately as they do in ordinary Euclidean space, within observational precision. Near flatness does not prove infinity. A space can be so large that its curvature is undetectable within the observable region, and some possible global topologies can be finite while remaining locally flat. The data constrain geometry across what we can observe. They do not grant a view of the totality beyond every horizon. This is where scientific restraint becomes part of the wonder. Cosmology can measure tiny patterns in ancient radiation, infer the development of structure, and test geometry across enormous scales. It can also state clearly where observation ends and which conclusions do not follow from the evidence. From the spacecraft window, the observable universe may feel like everything because everything you know arrives through it. But reality is not required to fit inside the region that has communicated with you. There may be far more beyond the present horizon, perhaps governed by the same broad conditions, perhaps containing histories whose light will never enter your instruments. The honest answer is not a picture of a wall. It is an acknowledged limit. Turn the spacecraft now toward a nearer and more localized horizon, the boundary around a black hole. Unlike a cosmological horizon, an event horizon around a black hole can be approached within a particular system. Yet it too is defined by causality rather than solid material. Near it, clocks carried along different paths reveal how deeply time belongs to space-time geometry. Far ahead, a black hole moves against a field of background stars. The object itself emits no ordinary light, but nearby gas and the distortion of more distant images reveal the gravity of the region. Your spacecraft remains at a safe distance while a small robotic probe begins falling inward. Both ship and probe carry identical clocks. Before release, the displays agree. Once their paths separate, there is no requirement that they accumulate the same amount of elapsed time. In relativity, each clock measures proper time along its own route through space-time. Motion matters, gravity matters, and the full path matters. The probe transmits one signal after every tick. At first, the pulses arrive regularly. As it falls deeper, the ship receives them farther apart and shifted toward longer wavelengths. Each message carries less energy. The probe appears to slow, redden, and fade. From your distant viewpoint, the final approach to the horizon never arrives as one bright, sharply observed crossing. Signals become increasingly delayed and difficult to detect. This behavior is often described by saying that the falling object freezes at the horizon, but the phrase can create a false picture. What freezes is not the probe's own experience. The distant observer receives an ever slower and fainter record. On board the probe, the local clock continues ticking normally. nearby instruments behave as expected. If the black hole is sufficiently large and the probe crosses an otherwise quiet horizon, there may be no local flash or solid boundary announcing the moment. The event horizon is not a surface made of matter. It is the causal boundary beyond which future directed paths cannot carry the probe back to the outside universe. The two descriptions do not contradict each other. The ship organizes events using distant coordinates and received signals. The probe follows its own proper time. Relativity allows observers on different paths to compare events differently while maintaining consistent physical laws. Imagine that the probe could somehow transmit observations indefinitely, even though no signal sent after crossing could escape. Before the crossing, each message would climb outward through the gravitational field, losing energy and arriving more red-shifted. After the crossing, every possible future path for light remains directed farther inward. The absence of later messages is not a technical failure. It is part of the horizon's definition. Time dilation near the black hole is real, not an optical trick or damage to the clock. If clocks follow different routes and are later compared where comparison is possible, they can show different elapsed times. Similar effects, far weaker but measurable, occur around Earth and must be considered in precise timing systems. The black hole carries the same principle into a much stronger gravitational regime. A clock held at a fixed location near the horizon would require enormous acceleration to resist falling, and maintaining that position becomes impossible at the boundary itself. This is different from a freely falling clock, which follows a natural path through space-time. Statements about how fast a clock runs must therefore specify both where it is and how it is moving. The probe also encounters tidal forces. Gravity pulls more strongly on its nearer side than on its farther side. This difference stretches in one direction and compresses in others, an effect sometimes given the memorable name spaghettification. How severe the tides are at the horizon depends strongly on the black hole's mass. Around a stellar mass black hole, the gravitational field changes rapidly across a human-sized distance, and destructive tides can occur before or near horizon crossing. Around a sufficiently massive supermassive black hole, the horizon is much larger, and the change in gravity across the same small object can be comparatively gentle at that boundary. This produces a counterintuitive result. The more massive black hole can have a horizon that is locally less violent to cross, even though escape beyond it is equally impossible. Farther inward, tidal forces still grow, and the classical description eventually reaches regions where known physics cannot provide a complete account. Remain with the spacecraft, watching the probe's last detectable signals lengthen and fade. Nothing visible marks a universal clock slowing everywhere. Your clock continues normally. Distant stars evolve. The black hole follows its orbit. Time is not one master rhythm imposed equally across the cosmos. Every object carries its own duration along its path. Two travelers can depart, experience different motion and gravity, and later disagree about how much time has passed without either clock malfunctioning. The geometry between departure and reunion determines the difference. This is why phrases such as time stops require care. A clock does not feel itself stopping. A distant description near an idealized horizon can assign an ever later coordinate time to the crossing, while the falling traveler reaches and passes the horizon after a finite amount of personal time. The received light tells one part of the story, the local journey tells another. The probe has now vanished from every possible future conversation with the ship. Yet the black hole is not outside science. Astronomers measure the motions of nearby stars and gas, detect X-rays from hot accretion flows, image horizon-scale emission around supermassive objects, and observe gravitational waves from mergers. A dark boundary can be studied through everything it changes around it. The horizon should also be kept distinct from the central singularity predicted by an idealized classical solution. The horizon is a causal boundary that can exist far from the region where curvature becomes extreme. The singularity marks a breakdown in the classical description. Combining them into one surface erases the very structure relativity is trying to explain. Move away from the black hole and allow the clocks to recede from view. The journey has shown how geometry shapes time near an extreme object. The next destination lies in the opposite direction, not toward greater concentration, but toward an early universe filled almost uniformly with hot plasma. There, the question is not how clocks cross a horizon, but how matter became capable of forming the first stable atoms. Imagine that the spacecraft is no longer moving through distance, but through a reconstruction of the early universe. Galaxies dissolve. Stars disappear. Every direction becomes filled with a hot, nearly uniform plasma. There is no empty corridor through which the ship could travel, and no real spacecraft could survive the conditions. The viewpoint is a scientific instrument of imagination, allowing you to ask what matter was capable of becoming at that time. The familiar world depends on atoms. A chair holds its shape because atoms form bonds. Air behaves as a gas of atoms and molecules. Rock, metal, water, glass, and living tissue all require electrons to occupy stable arrangements around atomic nuclei. Remove that organization and ordinary chemistry disappears. In the hot early universe, nuclei and electrons moved too energetically for neutral atoms to remain stable in large numbers. An electron might approach a nucleus and become bound, only to be knocked free again by energetic radiation. Matter existed mainly as an ionized plasma, a state in which charged particles moved without the durable atomic structure surrounding you now. This does not mean that matter was disorganized in every sense. Physical laws still governed particle interactions. Nuclei had formed, radiation carried energy, gravity responded to density, and pressure influenced motion. But the particular level of structure called ordinary atomic chemistry was unavailable. Hydrogen nuclei were present, yet neutral hydrogen atoms could not persist. Helium nuclei existed, yet their electrons did not remain attached in the familiar way. There were no stable molecules of water because water requires atoms able to share electrons in chemical bonds. There were no mineral grains, no oceans, no atmosphere like Earth's, and no cell membranes. An atom is not a tiny solar system with an electron circling like a planet. Quantum mechanics describes allowed states and probabilities rather than a miniature orbit drawn around the nucleus. When an electron becomes bound, only certain energy arrangements are available. Transitions among them later produced the spectral lines astronomers use to identify elements across space. Expansion provided the route toward a new form of complexity. As the universe grew, the average energy of radiation fell. Collisions became less violent. Eventually, electrons could remain bound to nuclei for long periods, allowing neutral atoms to dominate. The transition was not matter suddenly appearing. The ingredients had already existed in other forms. What changed was their ability to remain organized. The same particles entered a new physical regime because temperature and density crossed conditions under which atomic binding became stable. Think of this as a set of doors becoming available. Before neutral atoms, many chemical pathways were closed. Once electrons could occupy stable states around nuclei, atoms could interact through electromagnetic forces in more elaborate ways. Later, under cooler and denser local conditions, molecules could form. Much later still, solid grains, planets, liquids, and complex chemistry became possible. Possible does not mean immediate. The first neutral atoms did not assemble into oceans or life. The early universe contained overwhelmingly hydrogen and helium, with only traces of a few other light nuclei. The richer elements needed for rocks and biology had not yet been produced in useful abundance. Atomic stability was therefore a prerequisite, not a completed world. It gave the universe a foundation on which later environments could build. Gravity still had to gather gas. Stars had to ignite. Nuclear reactions had to produce new elements. Dying stars had to return those elements to space, and later systems had to assemble from the enriched material. Look again at the surrounding plasma just before neutral atoms become common. Photons scatter repeatedly from free electrons. The universe is bright everywhere but visually opaque across long distances. There is no dark sky because there are no isolated luminous objects set against transparent space. Radiation and matter are closely coupled. As binding becomes stable, the scattering rate falls. Photons begin traveling freely, producing the ancient radiation encountered earlier in the journey. Here, however, the important change is not the microwave map. It is the arrival of durable atoms and the opening of chemical possibility. The most abundant atom is hydrogen, the simplest of all, one proton with one electron in its neutral form. Helium adds a more complex nucleus and another electron. These modest structures dominate the ordinary matter of the early cosmos. Their simplicity is a reminder that the universe did not begin with the full periodic table. An alphabet with only 2 common letters can produce repetition but limited vocabulary. In a similar way, hydrogen and helium can form structures and stars, but not the broad chemistry required for rocky worlds or known biology. The comparison is only a guide. Atoms do not combine with the freedom of written language. Quantum mechanics determines which bonds and reactions are allowed. Gravity gathers the neutral gas into denser regions. The first stars form from material with almost none of the elements astronomers call metals. Inside those stars, atomic nuclei will be stripped again by heat, and nuclear reactions will begin building new nuclei. Chemistry gives way temporarily to fusion, and fusion starts expanding the range of elements available to later generations. Between the release of the CMB and the first sustained starlight lies a period often called the cosmic dark ages. Neutral gas fills the universe, structure continues growing, and no ordinary stars yet illuminate the darkness. The name does not mean that nothing happens. Gravity is preparing the environments in which the first luminous objects can form. There is a rhythm to this history. Cooling allows atoms. Gravity heats gas inside stars. Nuclear reactions create heavier elements. Stellar ejecta cool again and allow those elements to enter molecules, dust, and planets. Matter repeatedly changes state while carrying the results of earlier stages forward. The spacecraft's imagined instruments now follow a cloud of primordial gas into one of the first stellar furnaces. Hydrogen and helium are about to become more than remnants of the hot early universe. Through nuclear reactions, stars will begin writing additional entries into the chemical inventory, making carbon, oxygen, and many of the materials from which later worlds are built. The cloud contracts under gravity. Its center becomes denser and hotter until hydrogen nuclei can participate in sustained fusion. A star has formed, and with it a new kind of cosmic workshop. Fusion releases energy because certain combinations of light nuclei produce more tightly bound nuclei, with a small difference in mass appearing as energy. For much of a star's active life, hydrogen is converted into helium through chains of nuclear reactions. The exact pathway depends on the star's mass and temperature, but the broad result is the same. A simple element becomes fuel for a heavier one. The early universe had already produced most of the hydrogen and helium. Stars did not invent those elements. Their chemical contribution becomes especially important when stellar interiors begin making nuclei that the hot Big Bang did not create in biologically or geologically useful abundance. Carbon is one example. During helium burning, stars can combine helium nuclei through a sequence that produces carbon. Additional reactions can transform some carbon into oxygen. The balance depends on stellar conditions, and different masses follow different evolutionary paths. Oxygen production is strongly associated with massive stars, which reach temperatures allowing successive stages of fusion. Their interiors develop layered regions where different reactions dominate. The common image of an onion can help describe those shells, though a star is dynamic rather than a neatly separated vegetable. Convection, mixing, rotation, and mass loss complicate the boundaries. As massive stars evolve, they can build nuclei toward the iron group in their deepest regions. Fusion beyond iron does not release energy in the same straightforward way as fusing lighter nuclei, so an iron-rich core marks a critical limit for ordinary stellar energy support. Iron itself does not come from one universal root. Core collapse supernovae contribute iron group material through advanced burning and explosive reactions. Type 1a supernovae, involving the thermonuclear disruption of a white dwarf in a binary system, provide another major channel. Several astrophysical environments contribute to the inventory measured in galaxies and planets. The same is true across the periodic table. Calcium in bones, carbon in cells, oxygen in water, and iron in blood trace to different nuclear pathways and different kinds of stellar histories. No single star forged every element now present in a human body. Think of the periodic table as supplied by several workshops. The hot, early universe produced mainly the lightest nuclei. Long-lived stars manufactured and released some elements through winds and late evolutionary stages. Massive stars built others and scattered them through powerful explosions. White dwarf supernovae added their own products. Still heavier nuclei can arise through processes involving rapid captures of neutrons in rare, energetic environments. The workshops are not planned factories, and their output overlaps. The same element may have more than one origin. Astronomers estimate those contributions by studying nuclear physics, stellar models, supernova remnants, spectra, meteorites, and the chemical patterns of stars born at different times. Starlight makes this history measurable. Each element leaves characteristic absorption or emission features in a spectrum. By comparing those patterns with laboratory physics, astronomers can study the composition of a star they will never sample directly. Large surveys then turn individual spectra into a chemical map of galactic evolution. A star does not need to explode to enrich space. Stellar winds can carry material away during several phases of evolution. Lower and intermediate mass stars can shed outer layers, creating planetary nebulae and returning carbon, nitrogen, and other products to the interstellar medium. Massive stars can lose substantial mass before their final collapse. When enriched gas mixes with surrounding material, later stars form with a broader chemical inventory than their predecessors. Astronomers use the term metallicity for the abundance of elements heavier than helium, even when those elements would not be called metals in everyday chemistry. Older stellar populations tend to have lower metallicity because they formed before many generations of enrichment. But age and metallicity are not identical. A star can form from unusually enriched or unusually pristine gas depending on its environment. Chemical abundance is a historical clue, not a perfect clock. Return to the spacecraft and fly through a cloud seeded by earlier stars. Tiny solid grains contain silicates, carbon compounds, and metals. Gas carries oxygen, carbon, nitrogen, and many other species. Shock waves and radiation reshape the cloud. Gravity gathers part of it into a new stellar system. Rocky planets require an inventory that primordial gas could not provide. Oxygen, silicon, magnesium, iron, aluminum, calcium, and other elements must be available in solid material. As galaxies became chemically enriched, the ingredients for such planets became more common. That does not mean rocky planets waited for one precise metallicity threshold. Planets can form across a broad range of environments, and the relationship between composition and planetary architecture is complex. The reliable point is that a universe containing only hydrogen and helium could not build an Earth-like rocky world. Nor did chemical enrichment guarantee life. Carbon allows an immense range of compounds. Water can serve as a versatile solvent. Rocky surfaces and atmospheres create varied environments. But possibility is not destiny. Biology requires suitable conditions and a history that cannot be inferred from ingredients alone. The phrase "made of stardust" captures part of this story. Many elements in bodies and planets were indeed forged in stars or stellar explosions. But the phrase becomes false when expanded to every atom. Much of the hydrogen in water and living tissue is primordial, formed from material whose nuclei date back to the early universe. Your body therefore carries more than one cosmic inheritance. Some nuclei are older than the first stars. Others were assembled inside stars that lived and died before the sun formed. They met in the solar system, entered Earth, circulated through rock, ocean, air, and life, and for a time became part of you. The spacecraft follows the enriched cloud as it collapses into a rotating disk around a young sun. Dust grains collide and stick. Larger bodies gather. A rocky planet begins taking shape from material with many previous addresses. The universe has learned enough chemistry to build Earth, though nothing in the process was aimed toward that result. Imagine the spacecraft arriving above the young solar system, long before oceans or continents exist. The sun is surrounded by a disk of gas and dust inherited from the Milky Way. Within that disk are products of the hot, early universe, material expelled by earlier stars, and grains transformed during their journey through interstellar space. Earth begins within this mixture. Dust particles collide and sometimes adhere. Small aggregates become planetesimals. Gravity allows larger bodies to collect more material, while repeated impacts, heating, melting, and differentiation reshape the growing planet. No atom carries a label describing its route. One iron nucleus may have formed through an explosive stellar process and later passed through interstellar gas, a dust grain, an asteroid, and molten rock. Another may have followed a different path. The exact biography of an individual atom is generally lost, but the collective chemical evidence reveals a recycled origin. Earth is therefore less like an object made from newly manufactured parts than a city rebuilt from materials that belong to older structures. Even that comparison has limits. Atoms are not always preserved like unchanged bricks. Radioactive decay, nuclear reactions, chemical transformations, and impacts can alter both nuclei and their arrangements. As the planet grows, dense iron-rich material sinks toward the interior, while lighter silicates contribute to the mantle and crust. Volatile compounds arrive, escape, react, or become trapped. The early atmosphere changes repeatedly. Water accumulates through a mixture of sources and processes still studied through isotopes, meteorites, planetary models, and observations of other young systems. The word source can refer both to the bodies that delivered material and to the chemistry that produced its ingredients. Asteroids, early planetesimals, interior outgassing, and other reservoirs may all matter to Earth's water history. Isotopic ratios help constrain their contributions, but the story is not reduced to one dramatic delivery event. Every water molecule combines hydrogen with oxygen, but those elements have different cosmic histories. Much hydrogen is primordial, descending from the early universe. Oxygen was made later through stellar nucleosynthesis and dispersed into space. Water joins an ancient nucleus with a product of stars. That simple molecule therefore corrects a popular sentence. Not every atom in your body was forged inside a star. The oxygen in bodily water has a stellar history, while many of its hydrogen nuclei predate the stars. A more accurate statement is also more interesting. You contain matter from several eras of the universe. Look down as Earth cools. A crust forms and is reworked. Water moves among atmosphere, ocean, ice, rock, and eventually living systems. Carbon cycles through air, minerals, seawater, and organisms. Plate tectonics carries material downward and returns other material through volcanism. Erosion dismantles mountains and builds sediments elsewhere. The planet is not a permanent arrangement of fixed pieces. It is a changing pattern in ancient matter. The atoms in a shoreline, a cloud, or a living cell may later occupy completely different environments. Temporary does not mean unreal. The structures are measurable and consequential while they persist. Life appears late in this chemical history, after billions of years of cosmic enrichment and planetary evolution. Carbon-based chemistry depends on carbon. Familiar metabolism depends on a range of elements. Cells require stable atoms, molecules, energy gradients, and environments where complex reactions can continue. Yet the existence of ingredients does not make biology inevitable. A kitchen containing flour and water does not guarantee bread, and cosmic chemistry is far more demanding than cooking. The origin of life remains an active scientific problem involving chemistry, geology, planetary conditions, and time. From orbit, the mature Earth displays a surface unlike any known elsewhere. Liquid oceans reflect sunlight. An atmosphere filters and redistributes energy. Life has altered the chemistry of air, water, and rock. These features emerged from local history, but their materials connect the planet to the wider cosmos. The iron in the core, silicon in the mantle, oxygen in the oceans, carbon in living tissue, and hydrogen throughout the planet do not share one birthplace. Earth assembled them into one world. The solar system became a meeting place for nuclei created in different environments and at different times. This is why studying meteorites matters. Some preserve early solar system material less altered than most terrestrial rocks. Their isotopic patterns reveal ages, heating histories, and contributions from nucleosynthetic processes that occurred before the Sun. A fragment small enough to hold can contain evidence of vanished stars. The same connection extends beyond Earth. Astronomers observe disks around young stars, identify molecules in interstellar clouds, and measure the compositions of stellar atmospheres. Planet formation is not isolated from galactic history. It is one stage in the circulation of matter through stars, clouds, disks, and worlds. Imagine following a carbon atom backward from a leaf. Before the plant, it may have moved through atmospheric carbon dioxide. Earlier, it could have been dissolved in an ocean, locked in rock, released by volcanism, or stored in another organism. Farther back, its nucleus entered the solar nebula after being produced and expelled by an earlier star. Follow a hydrogen nucleus from the same living tissue, and the path extends deeper still. It may have passed through water, ice, gas, and countless chemical reactions without losing its nuclear identity. Its origin reaches toward the first minutes of the hot, early universe, before stars existed to claim credit. Earth gathers these histories without erasing them completely. Isotopes, elemental abundances, mineral structures, and astronomical observations allow scientists to reconstruct portions of the route. Matter does not remember in a conscious sense. Its measurable properties preserve evidence. Now let the spacecraft withdraw until Earth becomes a blue point beside the Sun. The planet looks self-contained, yet almost every part of it refers outward to primordial nucleosynthesis, stellar interiors, supernovae, interstellar clouds, and the formation of the Milky Way. To understand how all of those stages fit within one cosmic history, the journey must return to a phrase often used as though it described a single event at a single place: the Big Bang. The name is memorable, but it can suggest the wrong picture. What began was not debris exploding from a center into an empty room. It was an early state in which the universe itself was hot, dense, and evolving everywhere we can trace. Keep Earth as a small point behind the spacecraft and allow the surrounding map to run backward. Galaxies draw closer on average. The cosmic web becomes less developed. Stars disappear, atoms ionize, and matter approaches the hot plasma encountered earlier. Every region in the observable universe participates in this reversal. This is the central meaning of the hot Big Bang model. It describes an early universe that was hotter, denser, and expanding from conditions unlike those observed today. It does not describe a bomb detonating at one location and throwing matter into pre-existing empty space. An ordinary explosion has a center. Debris moves outward through an environment that was already there. Observers can stand outside the blast and point toward its origin. Cosmic expansion does not require any of those features. From Earth, distant galaxies show a broad expansion pattern. An observer in another galaxy would see a similar large-scale pattern centered on that location. This is possible because the expansion is not motion away from one privileged point within space. It is an evolution of large-scale distances throughout the modeled universe. Imagine a coordinate grid drawn only as a mathematical aid. As cosmic time advances, the scale associated with separation changes. Galaxies embedded in the large-scale flow become farther apart without being fragments launched from one square on the grid. The drawing should not be mistaken for reality. Paper has edges and sits in a larger room. The cosmological model does not require an external room into which the grid expands. This also changes the question: what happened before the Big Bang? The phrase Big Bang can refer to the hot, dense early phase described by well-tested cosmology, or it can be used loosely for an absolute beginning. Those meanings are not identical. Observations strongly support a history in which the universe expanded and cooled from a much hotter state. The CMB, light element abundances, galaxy evolution, and large-scale expansion fit that framework. But tracing the equations backward eventually reaches conditions where known theories cannot be trusted without a quantum description of gravity. The agreement is powerful because the evidence comes from different eras. Nuclear calculations account for the broad primordial production of light elements. Ancient radiation records the later transition to transparency. Galaxies and expansion measurements trace billions of years of subsequent evolution. One model connects them without claiming to describe every unknown at the beginning. Classical general relativity can produce a singular limit when extrapolated far enough backward. A singularity in the mathematics is not a photographed object or a confirmed physical point where science has observed everything begin. It often signals that the classical theory has been pushed beyond the domain where it can provide a complete description. The cautious conclusion is not that nothing can be said, and not that the absolute beginning is known. Physics describes later early universe stages with impressive precision. As the reconstruction approaches more extreme energies and earlier times, uncertainty grows, and the need for deeper theory becomes unavoidable. Inflation is one proposal for an extraordinarily early period of accelerated expansion. In many models, it can help explain why distant regions of the observable universe have closely related properties, why large-scale spatial curvature is so small, and how tiny primordial perturbations could arise and later seed structure. The idea connects several observations elegantly. Measurements of the CMB are consistent with important predictions shared by broad classes of inflationary models. Yet consistency is not the same as direct identification. Scientists have not discovered the specific field, mechanism, or unique microphysical model responsible for inflation. Some possible signatures remain under active investigation. Different inflationary models can produce different patterns, and alternatives may address portions of the same evidence. A documentary should therefore avoid saying that inflation has been directly seen. It is a powerful and influential framework whose underlying physics remains unresolved. The common picture of inflation, smoothing or flattening the observable region, also needs care. Enlarge a tiny patch of a curved surface enough, and it can appear nearly flat. Rapid expansion offers a related intuition for why measurable curvature could become extremely small. But the analogy does not prove that inflation occurred, nor does near-flat geometry prove that the entire universe is infinite. Now picture the spacecraft trying to mark the location where the Big Bang happened. Every point in the present cosmic map traces back toward hotter, denser conditions. There is no single direction to travel. The event was not over there. In standard homogeneous cosmology, the early state belonged everywhere to the region that later became observable. Nor can the ship move outside the universe to watch expansion from a distance. The model concerns space-time itself. Asking what it expands into may import an everyday idea of objects requiring surrounding space, when the geometry being discussed is already the framework in which distance is defined. These statements do not settle the global shape or total extent of reality. The entire universe may be far larger than the observable region. Its topology may contain features beyond current detection. Some theoretical models propose earlier phases, bounces, cycles, quantum origins, or larger structures. None has yet become a confirmed extension that licenses a simple final story. Scientific honesty leaves the boundary open. The hot Big Bang model is not weakened by admitting what it does not describe. Its success lies in connecting expansion, ancient radiation, light elements, and structure across cosmic history. Its limit lies in the earliest regime, where a tested account of gravity and quantum physics has not yet been achieved. From the spacecraft, run time forward once more. Plasma cools, atoms form, stars ignite, galaxies assemble, heavy elements spread, a solar system appears, and Earth becomes capable of hosting observers who reconstruct the sequence from light and matter. The Big Bang is therefore not merely a remote first scene. It remains present in the abundance of hydrogen, in the microwave background, in the expansion of distant galaxies, and in the initial conditions from which structure grew. The early universe did not stay early. Its properties became the starting conditions for everything that followed. Now continue the clock beyond the present. Galaxies evolve, stars consume fuel, and accelerated expansion changes which regions remain in contact. The future cannot be observed directly, but physical models can extend known processes forward. Their predictions become less certain as the extrapolation grows longer, and the final chapter must keep that uncertainty visible. Imagine the spacecraft remaining intact while cosmic time accelerates around it. Constellations lose their familiar shapes. Stars move, age, and die. New ones continue forming in cold molecular clouds, but the overall rate of star formation across the universe is already lower than it was during its broad peak billions of years ago. Galaxies have not run out of activity. Gas continues to cool in some regions. Stars are born in the Milky Way and elsewhere. Mergers can compress material or deliver new supplies. Yet the cosmic trend has declined as available cold gas is consumed, heated, expelled, or made less able to collapse. Run the clock farther forward, and the bright, short-lived stars disappear first. Massive stars burn through fuel quickly. Smaller stars use their reserves more slowly. Red dwarfs, faint enough to have hidden from the naked eye in the opening chapter, become increasingly important in the long future. Models suggest that the lowest mass red dwarfs can remain luminous for trillions of years, vastly longer than the universe has existed so far. No such star has completed its full life because the cosmos is not yet old enough. Their ultimate behavior is therefore a theoretical extrapolation based on stellar physics, not a history astronomers have watched. The night sky of that era would differ from today's. Bound galaxies may have merged and rearranged. Star formation would become rarer. Stellar remnants such as white dwarfs, neutron stars, and black holes would represent a growing share of what remains after ordinary stars exhaust their fuel. Accelerated expansion changes the wider view. Galaxies gravitationally bound within a local system can remain together, but sufficiently distant unbound systems recede farther away. In a future governed indefinitely by something like a cosmological constant, more of the external universe passes beyond practical observation and eventual communication. This does not mean expansion tears apart atoms, planets, or galaxies in the standard scenario. Bound structures resist the average cosmic flow. The future becomes isolated on large scales while remaining locally organized for immense periods. Imagine astronomers arising in a very distant era inside one surviving bound galaxy. Their sky may contain no accessible evidence of remote galaxies because expansion has carried those systems beyond visibility. The CMB would be stretched to wavelengths increasingly difficult to detect. Reconstructing the history of cosmic expansion could be far harder than it is for observers today. Our era is therefore unusual in an observational sense. We live late enough for galaxies, heavy elements, planets, and complex instruments to exist, yet early enough that ancient radiation and a broad population of distant galaxies remain available for study. The universe has not chosen this time for us. It is simply the interval in which our observations happen to be possible. Eventually, under leading models, usable energy differences become harder to find. Stars provide hot reservoirs against cold surroundings. Accretion disks, chemical reactions, and gravitational collapse all depend on gradients that allow energy to flow and work to be performed. As systems approach equilibrium, those differences diminish. Heat death is the name often given to a limit in which useful free energy gradients have become extremely scarce. It does not mean that the universe catches fire. Energy may still exist, but without accessible differences, it cannot readily drive organized change, much like a battery whose terminals have reached the same potential. The battery comparison is incomplete. Cosmic thermodynamics includes gravity, horizons, quantum fields, and an evolving space-time. The idea it preserves is narrower. Energy alone is not enough. Work requires differences that can be exploited. Heat death is also model-dependent. It follows from extending current physical understanding and a particular long-term expansion history across durations no observation can test directly. The farther the prediction reaches, the more it depends on assumptions about particles, gravity, dark energy, and processes that may not be fully understood. Other possible endings receive dramatic names. A big rip can occur in certain models where the effect driving acceleration strengthens enough to overcome bound structures. Vacuum decay refers to a hypothetical transition in the state of quantum fields. Cyclic or bouncing cosmologies propose different large-scale histories. These ideas are not equally supported, and none should be narrated as an approaching confirmed event. Even familiar far-future claims require restraint. Proton decay has not been observed. Exact black hole evaporation timelines depend on mass and on applying theoretical physics across extraordinary durations. The final state of dark energy is unknown. A responsible forecast separates established processes, model-based extrapolations, and speculation. Allow the imagined future to slow. The spacecraft returns to the present, where stars still fill galaxies and the cosmic microwave background remains detectable. The moon is again only a little more than 1 light second away. Distant galaxies continue sending ancient light across expanding space. Look back toward Earth. Every part of the journey converges on that small world. Its darkness revealed the limits of human vision. Its telescopes recovered the oldest freely traveling light. Its physicists inferred invisible matter from motion and lensing, measured expansion through spectra, and learned that clocks do not share one universal rhythm. The planet itself is assembled from the history it studies. Primordial hydrogen moves through its oceans and living cells. Oxygen, carbon, silicon, calcium, and iron carry the results of stellar evolution. The atoms are ancient, but their present arrangement is temporary and active. There is no need to say that the universe remembers. Matter has no intention to preserve a story for us. Instead, physical evidence remains. Wavelengths, isotope ratios, orbital motions, background radiation, elemental abundances, and patterns across galaxies. Patient measurement turns those traces into a partial history. The history is partial because every observer has limits. We see along one past light cone. Horizons restrict which events can communicate with us. The earliest regimes exceed tested theory, and the distant future depends on extrapolation. Knowledge grows not by hiding those boundaries, but by defining them more carefully. From the observation window, the universe is no longer a collection of 100 disconnected facts. The darkness between stars connects to cosmic history. The microwave background connects to atoms. Early variations connect to dark matter and the cosmic web. Galaxies connect to stellar furnaces. Those furnaces connect to Earth, and Earth connects back to observers studying the light. For a brief interval, ancient matter has gathered into instruments and minds capable of asking where it came from. The answer is not complete, but it reaches across nearly the entire observable history of the cosmos. Outside the spacecraft, the view remains quiet. Photons continue arriving from the moon, the stars, distant galaxies, and the early universe. Each has crossed a different distance and carried a different age to the same window. The universe does not reveal itself all at once. It arrives as evidence, and for now, we are here to receive it.